Architecturally exposed structural steel. Design with detail. Part 4. Custom steel. This presentation is brought to you by the Association of Collegiate Schools of Architecture. My name is Terri Meyer Boake. I teach architecture at the University of Waterloo, and my passion is steel. When designing with architecturally exposed structural steel, designers look to custom fabrication when the use of standard hot-rolled sections or tubes is incapable of meeting the aspirations of the design. This is characteristic of much of the work of Santiago Calatrava, as can be seen in the complex angled and curved geometries of the Orient Station. The long glass-covered cantilevered canopies of the bus waiting area at Orient Station required the use of custom steel to fabricate the cantilever support system. Although in section the elements retain the characteristic web and flange arrangement of a standard beam, the web dimensions vary significantly to suit the loading and load paths of the cantilever arrangement. Additional web reinforcing is applied as needed. A closer view of the canopy reveals the use of welded plate steel to create the structure, even to the cantilevered supports that support the glass roof. A detailing language has been established that is quite consistent and adaptable to the various scales of the members. Again, although the sections may appear as wide flange members, they are all custom fabricated from plate steel. The train shed at Orient Station takes on a different configuration, abandoning the long cantilevers of the bus shelters and assuming an evenly spaced tree column arrangement. Again, the members reflect a wide flange section type, but the varied forms required to create the tree-like form have been fabricated from custom cut and welded plate steel. This project would have required significant site welding during the erection process. The Siemens Crystal by Wilkinson Air Architects uses plate steel to create these unusual trapezoidal columns and beams. The structure is unusual in the omission of intermediate purlin members, asking the steel decking to span unassisted from beam to beam. This gives a much cleaner look to the structure of the exposed ceiling. The design is focused on offsetting or setting meeting planes of steel back from each other in the creation of corners. This has avoided the need for excessive grinding, as the connection can be done using fillet welds. The resulting shadow line provides visual detail. The observation platform at the Shard by Renzo Piano again uses architecturally exposed structural steel that takes on the appearance of wide flange sections, but in order to respond to loading and a desire for crisp corners, fabricates all from plate material. The use of plate material is easily identified by the crispness of the corners, as hot-rolled sections have a roundness to the shape as a result of the rolling process. In this detail, it can be seen that the corner column is fabricated as a box column, and the plates are inset to create consistent detailing, as well as an easier-to-fabricate welded corner. The plates that form the flanges at the top of the bracing members have been gently curved to resolve more gracefully the intersection between the diagonal brace and the beam. The bolted connections allow for quicker on-site assembly. The braced steel exoskeleton of the New York Times building, also by Renzo Piano, carries through the use of custom plate steel in the creation of the support system. Again, plate steel is used to ensure crisp corners as well as to respond to loading in geometric configurations that would be difficult using standard hot-rolled members. This creates obvious increases in project costs and so is limited to projects that warrant such custom work. The Leadenhall building, also known as the Cheese Grater, by the office of Richard Rogers, uses custom steel to fabricate the large gray megaframe that comprises the office space, as well as the bright yellow steel frame that encloses the washroom and elevator core. The use of plate steel in the custom elements of the Leadenhall building allows for consistency in the geometry of the members and their connections, while also allowing for thickening of the plates to satisfy the loading. It is apparent in this detail that the flanges on the two members are significantly different, a reality that recedes from view when observing the overall building from grade. Similarly, the welds can be left unremediated, as they will be unnoticeable from the viewing distance. The use of custom plate steel allows the designer to adapt the detail to the varied geometric requirements of the trapezoidal tower to create a coherent aesthetic. This was the only solution to resolving 6 members joining at this nodal connection. The inverted K-bracing that stabilizes the Leadenhall building uses a different language for the details as a result of using hollow structural shapes. Although there is some sympathy in the design choices with the primary frame, an effort has been made to set the bracing system up in a distinct way. Pin connections using custom plate steel have been welded to standard HSS segments that form the main of the bracing members. The need to break the components into subsections that can be quickly assembled on site is evidenced by the bolted splices that are discreetly done between the HSS members. In the design of the large glazed facade for Museum, custom ACSA trusses were used to support the stainless steel cable system that in turn supports the mullionless glazing system. Vertical trusses sit at either end of the facade and are used to provide resistance to the cables that span between the trusses and tension the facade. This is an important architectural element for the space and required customization to provide the attachment points for the cables. This intersection between the cable-supported glazing system and the vertical steel truss shows the level of precision required, as well as the use of plate steel to create the truss. The pair of plates that comprise the truss are structurally joined by another steel plate that sits back from the face, allowing simple fillet welding for the construction. The use of plate steel allows for very sharp corners. The design of Cannon Street Station was quite challenging, as it required the creation of a significant cantilever over the access point to the London Underground. The right side elevation serves as a large truss to achieve this cantilever. A different approach to bracing along the street face at the left side of the image incorporated a variation of the same aesthetic language. The large bracing members were fabricated from custom steel plate and HSS tubes. The plate sections again set the joining plates for the front face back from the sides of the box to create a simple fillet welded detail and an elegant shadow line. Less expensive HSS tubes were employed as the shorter bracing members. The detail at the upper corner of the exostructure reveals the level of complexity of the joint, as well as the transition from the use of square sections on the truss side of the building to round sections at the street face, with the large round vertical tube with the conical end acting to separate the facades. The front facade then uses more standard round HSS members that are more aesthetically in tune with the round diagonal braces. The rounded geometry works better with the clefts attachments that are used on the tension bracing. This close-up also shows the discrete bolted connections on the vertical members. The language of connection of the HSS tubes, be they square or circular, is consistent on both facades. This connection allows for easier on-site assembly of the structure and a high degree of prefabrication of the elements at the shop. Additionally, the slight curvature of the large sections of the truss side is more readily accommodated using custom plate steel for the members. This railway station in Guangzhou, China, makes use of a variety of custom structural systems and custom steelwork to fabricate the various function areas of the station. Consistency in the application of the connection language is always desired. Here we can see a similar tension bracing system used for the roof and glazed lattice areas. Where the trusses that span over the roof area of the station have been fabricated from round HSS tubes, the angular supports are using plate material to create the rounded trapezoidal columns. Anytime you see a tapered section, be it rectangular or round, this will indicate the need for custom fabrication, as these are never standard. The ABC Museum creates a very innovative truss using plate steel. The box truss is fabricated with an uneven diagonal grid of plate members that are connected via welding. Members in one direction are continuous from the top to the bottom, and in the transverse direction are carefully cut and welded to create clean lines. Here is a view to the underside of the truss, showing the nature of the simply welded connections. Fabrication increases in difficulty when the angles become too acute, so this needs to be controlled in order to prevent impossible conditions for welding. The extensive desire for curvature, combined with asymmetrical geometries, can call for the use of custom fabrication. In the case of the Amgen Helix Bridge, the large tubular supports are extremely tilted and also require custom bending for the large standard tubes. The fall prevention system at the sides of the bridge also uses curvature, and the design and sizing of these components asks for a custom solution. The view down the center of the bridge highlights the variety in shape and size of the round HSS ladder-like trusses that connect the walking platform to the large arches. A tapered cone is used to connect the large round tubular arches to their round tubular supports at the base, making for a smooth transition. Cones are always custom fabricated through a system of break forming. The Arganzuela Bridge is quite unique in its application of curved steel to create the box sections of this round tubular truss bridge. A high level of site welding was carried out, so the overall design detailing needed to factor this into the cost. The curvature of the box sections would be best achieved by plate rolling. As the designers wanted actual corners, the notion of insetting the plates and fillet welding was not used. Instead, the corners are welded and the welds have been left unremediated. Where this detail might be unacceptable in some circumstances, the understanding of the extreme cost to grind the welds, combined with the stippled effect of the lighting, led to a decision to let these remain as is. The result is a very spectacular pedestrian bridge experience. The cultural complex in Valencia, Spain by Santiago Calatrava makes widespread use of ACSA along with concrete, tile, vegetation, and water. These angled supports, which are very organic in nature, only reveal themselves as steel upon very close examination. Such shaping has been done using plate steel and varied bending processes, along with welding and much grinding and remediation. This level of workmanship drives up the costs of projects. The canopy over the garden is created from custom-formed members that are made to appear like wide-flanged sections of varying width that have been joined with a network of solid steel rods that are welded to the webs of the curved arches. The effect is highly successful. Each of the buildings on the site makes use of expressed steel in different ways with different details. Here, steel is used to create a dynamic system that allows the opening and closing of the facade and doors. Where Calatrava interchanges steel and concrete on some of the larger structural components, steel is the only choice for this custom fabricated system. The mix of steel and concrete on the Valencia Science Museum is quite subtle. Here, though, the slenderness of the double-tapered verticals that run through the series of voids in the concrete frame set themselves apart due to their detailing and proportions. The application of custom work in architecturally exposed structural steel requires a high level of knowledge of fabrication processes in order to maximize the sculptural or crisp effects of the steel. The architect, engineer, and steel fabricator need to work closely to take the best decisions for the outcome of the project. I've only touched upon some of the basic ideas behind the use of custom fabricated steel in design. For more information and lots of case study examples and photos to inspire your work, feel free to connect with me on my ASS Facebook page. And for more detailed information on designing with steel, check out these books on the topic. They are filled with plenty of photos like the ones included in this presentation and more valuable tips on fabrication, erection, design, and detailing.